All right, one of the things that you find in digital sound design is a lot of composers start to, to take the information of how we create the parameters for sound, and we use something that broadly is called algorithmic composition, where we have the machine can do more than just be a passive sonic generator for what we put into the structures, but we can use the computer and the processing power of the computer to generate a lot of the information that determines the types of sounds and the structures of the sounds. So this is broadly referred to today as algorithmic composition procedures, but there are different subtle manifestations of that. Many composers like to work in what is called sonification, where they take complex scientific data, and rather than, say, visualize that data to try to understand what's in the information, they try to turn it into sound. So they sonify the data. And many times people who are involved in sonification are really driven by the question of what can I learn about that data by listening to it rather than looking at it in a visualized format. What I do, and I'll give you in this demonstration a little bit of a piece that I did, which I don't necessarily call it sonification is the technique I was using. I'll explain that. I call it data-driven composition, which is quite similar. So let's take a look at what is this idea of algorithmic composition. You know, algorithms is something that is embedded into people that use computers are working with certain kind of algorithms. Algorithms are formulas or rules for behavior that the computer can operate in. This is not something that started with computers. It goes way back. There's a lot of history of having machines that give us computational information. So in some ways we can go back to the abacus, which was found in Babylon and early medieval times, very popular as a way of counting. It was a system for giving us a way of understanding relationships, deterministic relationships, through some kind of machine that would guide us toward that information. So the idea of calculating machines is a very rich old history. Perhaps Leonardo da Vinci he explored the ideas of certain kind of counting machines in very different ways during the 16th century. Moving forward, there's another important person, John Napier, 1550 to 1670. John Napier was a Scottish mathematician, important for a number of reasons. Perhaps one of the most important was his use of or understanding of the logarithm. And the logarithm opened up all sorts of different ways of understanding mathematical relationships. And in some ways, if we want to understand when the equal-tempered tuning system that we use today in the West, the 12-tone equidistance tuning system, that really became popular once we have the logarithmic understanding for how to divide the scale into those 12 divisions, because it's a 12th root of 2 is how you have to calculate that. So John Napier is important for a number of reasons musically, but he was also interested. He designed a device for the multiplication and division based on the principle of a Pythagorean abacus. So from the mathematics, there's always been this understanding of, can we develop a more interesting kind of calculating machine that can give us information? Perhaps the most important thinker about mathematics and the machine was Gottfried Leibniz, 1646 to 1716. He invented something called a step reckoner. And this was a variable tooth roll that could move another wheel by up to 9 notches depending on its position. It's a very complicated machine that really opened the door for a very complicated kind of deterministic sense for how mathematical predictions could be made. It's not by chance that he was also interested in Chinese philosophy. He became very interested in a Chinese system of divination called I Ching. I Ching may be translated as Book of Changes. This is a system of hexagrams where you have these, in the I Ching system, you have various sticks that you keep dividing in kind of a random process to where you find out the answer to your question, and it gives you to one of these 6 hexagrams, or 64 hexagrams are emerged in that. So I Ching has been used in Chinese history as a predictive chance procedure for thousands of years. So we find Leibniz interested in the idea of how do we create a mathematical procedure, or how would we develop a machine that can be predictable or involve all the probabilities that you would find in a chance procedure such as I Ching. I Ching became fascinated by French artists, Mallarmé, poets. We also find John Cage in the 20th century becoming fascinated with I Ching and starting to compose using these systems. So this idea of deterministic moving to indeterministic mathematical models. In some ways, Leibniz was the first one which pointed us toward to understanding how do we develop systems, mathematical systems, and eventually machine systems that can be controlling algorithms to give us not just deterministic systems, but can give us probability or more chance-oriented systems. So then let's just look quickly at when does this whole field of algorithmic composition start to emerge. And that really started in the computer world as soon as we have computers. So if you look at 1955 to 1956, the very first completely computer-generated composition on a symbolic level was done by Lejeune Hiller and Leonard Isaacson, and it was called the Iliac Suite. It was built on the Iliac computer at the University of Illinois in 1955. This was one of the very first manifestations of the computer. So they developed a computer composition that was generated by that Iliac computer at that time. By 1963, then we have a lot of emerging languages and people approaching how do we develop a process that the computer can then determine what we want the composition to be and the digital sound elements of that. So by 1963, we have also Lejeune Hiller and working with Robert Baker developed really the first computer-assisted environment for composing, and this was called Music Comp, was what it's called. But very quickly after that, we have a number of people working on this idea. The 1970s, there were a number of things. Perhaps the groove system developed by Max Matthews and Richard Moore was an important one for algorithmic design. And then following that up with a number of programs, the 1980s we find Patchwork, which was developed at the French Center IRCAM. MIDI-less, Bull processor were probably the most popular ones. By the 1990s, Patchwork evolved into something called Open Music, which is I use that as my own compositional parameters today, but we have Common Music, Symbolic Composer. There were many other kind of systems that really took on how do we develop computer systems for generating and determining the elements of a composition. So today there are a number of computer languages, and some of those we're going to be introducing later in this course, but there are a lot of computer languages that today can be used for synthesis, for digital sound design processing, but also can be used for algorithmic design principles. So some of those would include what's called the Music-N family of languages developed by Max Matthews, C-Sound by Barry Vercoe, and then we have Pure Data, MaxMSP, Kima, Super Collider are some of the most common programs that are not designed specifically for algorithmic composition, but can be used for those purposes. So in algorithmic composition today, I'm not going to go through all of these. This is, I don't want to get too much in depth in this, but I just want to show you these are the various kinds of system approaches that people are using in trying to apply toward how do we compose music with some kind of rule-based system. So you can use Markov models, often involved in what are called hidden Markov models, which are predictive sort of algorithms embedded in some of the musical procedures. You can look at what's called generative grammars, and this is from Noam Chomsky. Many people have worked in this field of trying to understand how you can do language syntax as a way of understanding the sort of grammar of a computer language. Obviously, chaos theory has been an important part of people trying to emulate and model on chaos mathematics and butterfly effect and so forth, the kind of things that are involved in that mathematics. People have tried to apply into to design of musical principles. Biological models is perhaps one of the more popular ones today, and that I want to talk and give you information about a composition that I did recently, which tries to approach sort of biological or genetic models in trying to have a data orientation that then informs how the piece unfolds. Cellular automata, there are different ways of constructing sort of cells of ideas that have automated procedures through various kind of artificial neural networks is very popular. And then of course the research going on in artificial intelligence today in developing a sort of sense for how does our brain process information is an important part of what's happening in researchers who are coming from those fields who are designing algorithms that are based upon how we perceive sound. So in some ways this is an exciting time to be involved in this kind of research because we can start to build upon some of the information that we understand about how we perceive sound, what is happening in the brain when we have aesthetic experiences, when we have sensations of motion, or when we have pleasure or discord in our experience of sound. We're starting to understand that and then create models of that in artificial intelligence ways, which can develop algorithms for creating that. So in some ways there's a great interdisciplinary kind of research going on between the fields of mathematical understanding in the artificial intelligence community and what's happening in how we understand music cognition and perception. This is for Macintosh only, but this is a very simple, easy program you can download, developed by Paul Berg at the Institute of Sonology in The Hague. And it's a program called AC Toolbox, which he says, Paul says about this, is a computer-aided algorithmic composition is the broad area where computer tools are used to assist in the composition of musical material. The material could be limited to a handful of values useful for one parameter. It could be a framework of time and pitch values to serve as a basis for realizing a composition. Or it could be data for another program, such as a sound synthesis system. The material could be a complete description of a composer's model for a particular composition. So the AC Toolbox is essentially a collection of tools to facilitate various aspects of algorithmic composition. Several models of musical events are included in those toolboxes. So you can use this to shape objects such as sections, shapes, masks, note structures. So this toolbox is a way that you can generate a kind of a simple algorithms by certain specifications and then have the algorithm create different kind of musical devices through that. So if you do have access to a Macintosh computer, this is a good one to sort of play and try out to understand sort of simple ways of doing that. One of the things I mentioned is that in algorithmic composition, a lot of people are interested in trying to understand how data can function into controlling musical systems. So one of the fields that is called sonification. And sonification, here's a couple of information about this. This is definitions by Thomas Hermann, who works at the Center at the Ambient Intelligence Group at the Center for Excellence in Cognitive Interaction Technology at Bielefeld University in Germany. And here's his definition for sonification. Sonification is a technique that uses data as input and generates sound signals throughout the composition. So it is sonification if it follows these conditions. The sound reflects properties and relationships in the input data, so that whatever the data is, you can hear some kind of sound property that reflects that data. Number B, the transformation is systematic. This means that there is a precise definition of how interactions and data cause the sound to change, so that we can see as the data changes, there will be relationships between that and the changes to the sonic parameters. Number C, the sonification is reproducible. Given the same data and identical interaction triggers, the resulting sound may be structurally similar, so that if I change the data, we would hear very different sounds. If I go back to the original data, we would hear something very similar to that. So in order to have that relationship exist, the sonification needs to be reproducible in his mind. And finally, the system can intentionally be used with different data and also be used in repetition with the same data. So this idea of sonification in his mind is trying to understand how we would map this particular data into sounds, and certain kind of expectations and relationships are assumed in that. Here is a chart that Mr. Hermann developed, which is understanding how data can move into sonification, but it can be interpreted in different ways. You can have audification, you can have auditory icons, ear cons, you can have parameter mapping, model-based sonification, and then other novel techniques you have to be developed. So what I do in this is really work with the parameter mapping kind of sonification, where I try to understand in the data, can I map those aspects of the data into particular parameters of the sound synthesis that I'm designing? Or in some cases, can I model an acoustic instrument and what an acoustic instrument does and map that to sounds? So sonification opens up a lot of interesting possibilities. Here are some of the assumptions that you would find in doing sonification. It is the representation of some data through metaphorical structures of sound. We have to make some kind of connection that this data represents metaphorically this particular sonic parameter. So that's something the composer or the sonifier has to make those relationships. That's an assumption that has to be there. That absolute quantitative data is interpreted qualitatively, and that a successful sonification should efficiently convey the metrics of the source data without an inappropriate amount of listener fatigue. So if you are listening to this, it should be simple enough in a good sonification that as the data changes, you can hear quickly the data in the sound changes. You don't have to be listening so much going on complicatedly that you don't hear those significant changes. All right, so here's let's take a look at what is the relationship to data and sound. So in trying to create mappings, and what I'm trying to do here is, one of the things I have to look at is all the different parameters of how sound operates, and how do I determine the system of numbers, which is what the data is. How do I map those into interesting parameters of sound? So it could go into frequency, it could go into amplitude, we could have the data change the rhythm and the tempo. It could change the flow of the linear structures and the cadences of phrases. It could change the texture of the sound, foreground, middle ground, background. We could obviously change the parameters of timbre and how the sound is articulated. We could change the resonance characteristic of whatever instrument I'm creating. So later we'll get into physical modeling and understand how the sound of physical gestures of sound, we can map this data into those as well. We could have diffusion and spatialization be controlled by this. So we talked about the importance of how the location of sound is determined in our experience of that, but how does the data could shape those parameters? So when you are putting together some kind of sonification, or you're trying to do, in my case, what I would refer to as data-driven composition, I've got to make choices about all those different musical parameters and how I want to use this data to represent that, so that the listener, as those changes are occurring, will be aware that the data that I'm sonifying or deriving it from is affecting these parameters. So it's not a simple thing to do effective sonification.
The preceding program is copyrighted by Emory University.